Hello there, and this is time for the second part on a series on creating a evolution simulator. The big change that I've added is I've created a target. This is just another individual like all of the others with its own height, width, red, green, and blue values. However, it's whatever this is set to, all these individuals slowly move and mutate to become like that target value. Take a quick look over at the scene. Not a whole lot has changed. The population just has a population script with a couple more features that I'll go over the course of the video. The individuals are all just have that same individual script with a few changes, which we'll go over. And then I've added this target, which just has an individual script attached. When I click this change target button, the target changes to some other random value, and then these will start moving to change towards this new target. I can also click this randomize population to make them all go to a diverse state, which incidentally makes them get to the target much faster. I have a number of settings here. Inheritance type. So single inheritance is what we're using in the previous video, where each individual would pass its genes on directly, like a cloning kind of process. And then we also have a double inheritance where two parents' genes get spliced together to create the next generation. Mutation type, drift, this is what we were using before. There's also randomize, which just every single trait for every individual changes randomly. It's limited usefulness, but looks kind of nice. And then random mutation, where each trait has a chance of changing to anything within a random range. Drift amount, of course, only applies when this option's selected, and mutation chance only applies when random mutation is selected. Seconds per generation just determines how fast the simulation goes when I have the run tick box checked. Alright, so let's stop this and take a look at how all of this works. I'll start out by going into my individual script and point out a couple of changes. This was called single inheritance in the previous video. I've decided as I went forward that name wasn't very descriptive. I've renamed that to drift mutation, but it's the exact same method otherwise. I've added random mutation as an alternative way to change individuals, and how this works is for each trait, height, width, red, green, blue, I randomly have a random chance of mutating that trait. So if we take a look at what this method does, so I take a random floating point number between 0 and 1. If that happens to be less than the mutation chance, which is set here, then I set that value to some random point in the range between the low bound and the high bound, so that's these constant minimums and maximums that were set in the DNA. And if this condition doesn't happen, then we just return back the inherited value. It just gets the same as the parent. And we do the same thing with height, width, red, green, and blue, and then at the end, refresh the display. Everything else, this refresh display, the bound that's used by this drift mutation, all works the same. Well, the only other change is we've added this new data container called stats, which stores an individual's total fitness rating. So this works kind of like a reward function. Its rank between 1 and 64. Oh, that's another change you may have noticed in the scene. I've removed 2 individuals here and here. Before there were 66 individuals in the population, but it becomes important later on that it's a number that's easy to divide by 2 or 4 or whatever else I want to divide it by. So 64 works a little better, so I removed a couple. So it stores their rank between 1 and 64, and then also their offspring count, how many children in the next generation it'll a given individual pass its genes to. So that's it for the changes to the individual. Now let's move on to population, which really is the workhorse of this whole application. So we have our enumerations up here. This just sets all these four variables that the user can mess around with. Have our variables. This script was getting kind of long as I was writing it, so I delegated out a lot of functionality into these little helper classes: copy, DNA, utility, fitness evaluator, and new generation. I'll go over those as they come up. We have our parameters over here that the user can set, and then we have these user interface controls. If I was creating something a little bit more polished, I would have created the UI in the application itself, but for demonstration purposes, just having it available in the inspector works just fine. And then we have our population data, current population, the next generation, and a max fitness variable, which I'll go over shortly. On start, get the population, all the individuals the same way, and then we initialize the next generation in the same way. There's probably a more elegant and efficient way to do this, but for now this will work just fine, and it's nice and easy to read. Initialize some utility classes, and I'll go over those in a little bit. In the update method, we check for user input. That works mostly the same as before, except I've added a couple of new features here. If the user clicks change target, then target will randomize all of its traits. And remember, target is an individual just like all the other individuals, so it has access to this same method that just changes all its traits to some random values. And then if the user clicks this randomize population button, then it does basically the same thing to all of the individuals. So if we take a look at these two features in action, changing the target just changes that one target individual on the right side. And then when I randomize the population, it just changes all of them. Okay, so that's enough for user input and for updates. Now we'll take a look at this tick method, which is called every time the user clicks the step button, or if they have run selected, it happens based on an invoke repeating. This was covered in the previous video. So anyway, in tick, this part is not a whole lot different. For each individual, we evolve them, and this evolve, since there's several different options for evolution, each one calls a different method in the individual. So remember, this is happening for every single individual. So if they've chosen drift, then we call the drift mutation method, and which we've already gone over, and that passes in the drift amount, which has been set here. If they have randomize selected, then we randomize all traits, just set every trait to anywhere within their full range. And then if they clicked random mutation, then it goes to this one here, where it has some chance of setting each trait to a random value, but and that chance is set here. So if all of them fail that condition, then nothing changes. Okay, so that's how evolve individual works. So once all of the as the individuals are involved, we then compute their fitness. So here is where we start using our evaluator helper method, which is defined and initialized. It's declared up here, initialized in start, and here we're going to start using it. So if we look at this fitness evaluator, here's we just store a max fitness, have a reference to a target which is passed in by the constructor, and to compute max fitness, oh, actually I should go over that first. Back in start, the evaluator figured out what the max fitness rating is. And so that starts at 0, and it just looks at the spread between every trait. So the maximum height minus the minimum height, same for width, red, green, and blue. and adds them all together and gets a max fitness variable. And actually, if I take a look at that, that's going to be, let's see, 1.8 plus 1.8 plus 1 plus 1 plus 1, 3, yeah, so something like 6.6 or something like that. And anyway, we're going to use that later just so that we're working with positive numbers. So go back to this compute fitness, and this calculates a total error. So it starts at 0 and finds the difference between the individual's height and the target's height. So if we look at this difference, it's basically subtracting one minus the other, but with a bunch of mathf.abs's to make sure we're dealing with positive numbers all the way through. So that's how we find the difference between the heights, then do the same thing for the width, red, green, and blue. We add these all together, and that gets our total error. We subtract the maximum fitness from the total error. This should always be a positive number, and we store that in the individual's total fitness, or that's within their stats class. Remember, back in here. Okay, so that's how we compute the fitness. So we've gone through all the individuals, we've evolved them, and then we've assigned a fitness value to each of them. So once that's done, if we have the natural selection type of aimless, so if the user has chosen that, then they don't really care about the target, they don't care about their fitness value, so at this point we're actually done with our tick method and nothing more to say. If, on the other hand, they've selected something else, and right now the only other option is single target. I had some plans of adding multiple targets and doing something more complicated, but I don't think I'm going to bother with that. However, the option for expanding this is there, and I plan on putting all of this up on GitHub, and so you can take a closer look at some of this code, experiment around with it, and if you'd like to do something trickier with the selection type, like adding more targets, and each one gets to figure out which one it's closest to and gets its reward value based on that, or whatever else you come up with, have an open design that should make it not too difficult to extend. So anyway, though, back to this. So if it's not aimless, then we rank all of these we rank all the individuals in the population by their fitness value. So again, we're making use of this evaluator helper class, and here's how rank by fitness works. It takes in the population, and then I just use this array.sort, which is some kind of complicated syntax for it. Just go look it up. What this does, it sorts the individuals of the population by their total fitness value, and it's in descending order. You may notice that I use X, then Y here, and then Y, then X over here. That's what caused it to be descending. If I made this X and this Y, then it would be an ascending list. After this line, we have a sorted array. Now, once we have that sorted array, we can iterate through it and assign a rank to each one. So the first one in the list gets a rank of 1, the second in the list gets a rank of 2, and so on all the way up to 64. And I've made some little bit of modifications from the standard array convention. So using I equals 1 and I is less than equal, and an I minus 1 here. And all of that is so that I can start counting at 1, because starting counting at 0 is stupid. Just kidding. In this context, rank made more sense to start counting from 1, because that's the conventions of a ranking system. Anyway, moving on. So after we've ranked all of them by fitness, we have this nice list from 1 to 64, from the most fit to the least. Then we can apply natural selection to it. But one thing we're going to pass in to this natural selection is a selection pressure. So one of the variables the user has is selection pressure. They can have none, moderate, or heavy. I'm going to go with moderate for illustration purposes. And this just converts that enumeration value into a floating point number. So none is 1, moderate is 0.5, and heavy is 0.25. So if we look at apply natural selection, we have 3 basic steps. First, we assign a number of offspring to every member of the population, and then we create the next generation, and then finally we apply the next generation to the current population, and then so we can refresh the display and see them. Let's take a look at this assigning offspring method. And again, I'm using another helper class here of next generation. So I'm gonna, and that's initialized the same way as that evaluator. Take a look at assign offspring. Okay, here's our stores the data for population next generation. It's got its own utility class and a constructor right here for this copier, which I'll go over later. So anyway, assign offspring. It takes in a population and the selection pressure. So for moderate, remember that was 0.5, and it sets a cutoff rank. And this takes the size of the population times 0.5. So if this was 64, this is 0.5. The cutoff rank is going to be 32. And then I iterate through all the individuals in the population, and if their rank is less than or equal to the cutoff rank, then it's going to have 1 over pressure. So let's see, 0.5. This is going to come out to 2. So if it's ranked 1, 2, all the way up to 32, then it gets 2 offspring, or its offspring value in stats is set to 2. And if it's above the cutoff rank, then its offspring count is set to 0. Now, if I used a different selection pressure, say heavy, and that's had it return to 0.25 here, then the cutoff rank would be 16, and each individual that's below that cutoff rank or equal to it would get 4 offspring, 1 divided by 0.25, and the rest would have 0. So 17 through 64 would all have 0. So that's, now we've determined the number of offspring that every individual should have. We then use that to create the next generation. And this is going to receive current population, next generation array, and the inheritance type. So some initialization up here, including this, and then we'll go through all the individuals again. And if they have no offspring, we can just cut out of this and continue to the next. No calculations needed. Then if it has some offspring, then for however many it has, so if this number is 2, then this is going to be executed twice. If this is 4, this will be executed 4 times. This is just for iteration for this internal loop. And this is just a safety check to make sure we don't get any index out of range errors. This is the core method that really matters. It's how many times it's being called. So this create child is down here. And this looks at the inheritance type, which again is controlled by the user, single or double. And if it's single, then we refer to our copier utility and call the copy DNA method. So let's take a look at that copier. Here's our copy DNA class. So let's see, what method are we looking at? Yes, copy DNA. So this is pretty simple. It takes the DNA of the parent and the DNA of the child, and it goes step by step and applies the values from the parent to the child. I didn't really see a good, clean, easy way to copy all the values of a data class from one to the other. The default is to copy by reference, which causes all kinds of weird errors. So I just kind of do this manually right here. There may be some extension method or system out there to make this all in one line, but for only 5 values, this isn't too bad. Okay, so that's what happens if you're using a single type of inheritance. If you're using double or 2-parent inheritance, then we call the splice DNA method, and then this takes in, so this is the child's the first parent, and then just get some random individual. So let's take a look at the splice. This assigns values for the child's height, width, red, green, and blue, and it gets those from either the parents, the first parent, or the second parent. And remember that the first parent is the one that, you know, has this, that was called up here and has an offspring count because it's has a high enough rank. And then the other parent, I'm just getting some random individual. Just return some random individual out of the population. Doesn't matter which one, doesn't matter what rank they are, whether they're fit or not. In fact, there's even a 1 in 64 chance that this random individual will be the first parent, in which case this will be identical to this, this just copy. But that's only a 1 in 64 chance. It doesn't really break anything. I suppose if I wanted to be a little more fancy with this, then I could use something more complicated than just getting a random individual. But I find for simulation purposes this works fine. If you want to extend this by downloading the GitHub, this would be a great thing to play around with. Anyway, let's go back to splice DNA. So for each trait, taking a look at height, we randomize the trait. So basically this is just a coin toss, 50-50 chance that it'll get the first parent's value and 50-50 chance it'll get the second parent's value, and does that for height, width, red, green, and blue. So that's how the create next generation works. And next we go on to copying the population. So at this point we've specified all the DNA values for all of the individuals in next generation. Now we need to actually apply that so that we can see it. So go into this helper method, copy population, very straightforward. We just go through every individual and use this copy DNA method. There's a nice bit of reuse right here. And it's just put all the values in from the child and give it to the parent. Or from the next generation and give it to the current generation, I should say. That is all. So I'm actually going to end the video there as it's been running a little bit long. I imagine a lot of you will want to see what this looks like in action, and the next video will be covering exactly that. I'm going to be going through what happens when I pick each of these various options and see which one works better, the advantages and disadvantages of the different types, and just some interesting side effects, lessons learned about evolution. But I think I'd like to put that not in this video because some of the people who want to see this are not going to be very interested in going through all of the code. So I'm going to put all of the just fancy like display kind of stuff and non-technical things in its own video. If you like this video, you found the process interesting, feel like you maybe learned something from it, don't forget to like and subscribe to make this channel a little bit more visible and make sure that you get a notification when the next video comes out. And until next time, thanks for watching, and this is Will Patillo signing out.